Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Consider this scenario for a second. If you drive 100 miles in 2 hours, then your average speed is 50 miles per hour. But it doesn't mean that you're driving at 50 miles per hour the entire time. However, does that mean you were going exactly 50 miles per hour at some point? And the answer is yes. Even if you were at 100 miles per hour for half the time and 0 miles per hour for the other half, you had to cross that 50 miles per hour mark in order to get there. And this is known as the mean value theorem. Now, before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. The mean value theorem states we're going to let f be a function that satisfies the following hypotheses. The first one is that f is continuous on the closed interval AB. And then the second one is f is differentiable on the open interval AB. Then there's a number c that's in between AB such that f prime of c is equal to f of b minus f of a divided by b minus a. So notice that the right side is the average slope of the function f. So what we're saying is that there has to be a c in between a and b where the slope at that point is equal to the average slope of the function. Now notice that this looks very similar to Rolle's theorem that we introduced in the last video. And this is actually the generalized form of Rolle's theorem. It has removed the last condition, which is the equal endpoint requirement. So let's draw a diagram to illustrate what's happening here. Now let's say A is right over here and B is over here. And the requirements are that f is continuous on this closed interval and differentiable on this open interval. So it could look something like this. Now the average slope of this function in this interval is just the slope of the line that connects point A to point B. So here is f of b minus f of a over b minus a. And what the mean value theorem states is that there must be a number c within a and b such that the tangent line has the exact same slope. And in this case, we would have two such points. There is one roughly around here, and then another one roughly around here. So there could be multiple, but the mean value theorem guarantees at least one. So here we would have these 2 points where the tangent line has the same slope as the average slope. And now let's take a look at a couple of examples. For our first example, we want to find c for the function f of x is equal to x squared on the interval 0 to 2. So since this is our first example, let's go ahead and write everything out. Here we have our a is 0 and our b is 2. And then our f of a is going to be 0 squared, which is 0. And then our f of b is going to be 2 squared, which is equal to 4. So now notice that f of x is x squared, which is a polynomial. So therefore it is continuous and differentiable, which means we can apply the mean value theorem here. So now the average slope in this case is going to be equal to f of b minus f of a over b minus a. So this is equal to 4 minus 0 over 2 minus 0, which is equal to 2. So therefore, we want to find a c such that f prime of c is equal to 2, which means the first thing we need to do is to find the derivative of the function. So f prime of x is equal to 2x. And what we need is we need f prime of c to be equal to 2. So therefore 2 is equal to 2c, which means c is equal to 1. So this would be our final answer. For our second example, we're going to be doing the same thing. So our function this time is the square root of x minus 1. And notice that this function is continuous on the interval 1, 5. But we also need to make sure that it is differentiable on the open interval 1, 5. So let's go ahead and find our derivative first. So f prime of x is going to be equal to 1/2 times x minus 1 to the power of -1/2. So if we were to rewrite this, this is going to be 1 over 2 times the square root of x minus 1. And this is okay because this is defined on the open interval 1, 5, which means we can go ahead and use the mean value theorem here to find c. So we start with our average slope, and that is going to be equal to f of b minus f of a over b minus a. And here our b is 5. So this is going to be the square root of 5 minus 1 minus the square root of 1 minus 1 over 5 minus 1, which is 2 minus 0 over 4. So our average slope is 1 over 2. So now we just need to find c, where f prime of c is equal to 1/2. So f prime of c is 1 over 2 times square root of c minus 1. This is equal to 1/2. And then we're going to solve for c, which means 1 is equal to the square root of c minus 1. Squaring both sides will give us 1 is equal to c minus 1. So therefore, c is equal to 2. And for our last example, we're going to take a look at how the mean value theorem can be useful in certain proofs. Here, we want to show that this equation has exactly one real root. So notice that this is a 5th degree polynomial, and we have no easy way of solving for it, which is fine because we're not asked to find what the root is. We're just asked to show that there is exactly one real root. So there are actually 2 parts to this question. Part 1 is that we need to show existence. So meaning we need to show that there does exist at least one root. So part 1 is existence. And we're going to be showing that by using the intermediate value theorem. So we're going to let f of x be equal to 1 plus 2x plus x cubed plus 4x to the power of 5. Now f of 0 is going to be equal to 1. And f of negative 1 is going to be equal to 1 minus 2 minus 1 minus 4. So this is equal to negative 6. So now since f of x is a polynomial, we know that polynomials are continuous everywhere. So it is continuous. So because it's continuous and f of negative 1 is less than 0 and f of 0 is greater than 0, that means in order for us to go from negative to positive, we must cross 0 in between there. So that means there must exist a c within the interval negative 1, 0, where f of c is equal to 0. So now we have proved the first part, which is the existence of at least one real root. Now part 2 is where we prove that this root is actually unique, meaning that there's only this one root and there doesn't exist a second one. So part 2 is uniqueness. And we're going to be doing that through proof by contradiction using the mean value theorem. So we're going to start by supposing that there are 2 distinct roots. Distinct real roots, c and d. So this means we would have f of c is equal to 0 and f of d is equal to 0. Then, by the mean value theorem, we're going to get there must exist some number, let's call this number p, within our interval CD, such that f prime of p is equal to f of c minus f of d over c minus d. Now, since f of c and f of d are both 0, then that means this is equal to 0. However, let's take a look at what f prime of x actually is. So f prime of x is equal to 20x to the power of 4 plus 3x squared plus 2. Now notice how we have x to the power of 4 and x squared. And these are always going to be positive numbers because we have even exponents. So both of these are going to end up being positive numbers. And then our last constant term is a plus 2. So what this means is that f prime of x is going to be always greater than 0. And thus we have come to our contradiction, because by supposing that there are two distinct real roots c and d, we have said that there must exist a p where f prime of p is equal to 0. However, our derivative here says that f prime of x is going to be always greater than 0. And thus we have a contradiction, which means that our original assumption of there being two distinct roots must be false. So thus, we have proved that there is exactly one real root to our function f of x, which is why f of x equal to 0 has exactly one solution. And now let's do a quick recap of what we covered in this video. We went over the mean value theorem, which connects the average world to the instantaneous world. And geometrically, it means that there is a tangent line that is parallel to the secant line. But in order for us to use it, the function must be continuous on the closed interval and differentiable on the open interval. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.